Hello everyone, my name is Mete Atamel. I'm a developer advocate at Google in London. And this is my second time in Lviv. So I came here last year. One of my coworkers, she got an email from the organizers about DevFest in Ukraine, but she couldn't come. So she forwarded the email to me. And she asked me, you want to go to this DevFest in a place called Lviv? And at the time, I wasn't even sure where Lviv was, and I wasn't sure what DevFest were. But I accepted, I came, and then I was really amazed by the event here. I was expecting like a big meetup kind of thing, but it turned out to be one of the best DevFests I've been. And I like the people I met here and the amazing connections that I made with everyone. And one thing I really like about DevFest Ukraine is that it stays with you. What happened is that after DevFest Ukraine, I went to DevFest in Pilsen, and I saw a couple of the organizers from here in there, and I also went to Tel Aviv. There was one guy from Germany who spoke here that we met here. I went to Novosibirsk in Russia, and even there I met a speaker who I met here. So DevFest Ukraine is great, so I just want to thank the organizers for organizing such a great event, and it's great to be back. So today I'm going to talk about Apache Beam and Google Cloud Dataflow. If you want to get the slides, this is my Twitter right here. You can just follow me on Twitter, and I'll post the slides. And I also have my email, so if you have any questions, even after today, feel free to reach out to me. All right, so let's see if this works. Oh, it doesn't work because I had to turn it on. All right, so what's the premise of my talk? You know, sometimes I go to talks and then the speaker talks and talks and talks, but then you get to hear the big premise in the end. Well, I like to do it the other way around. So this is the premise. What is Apache Beam? Apache Beam is a single unified model for batch and stream processing. Okay? So what that means is that when you do big data processing, you have to choose what kind of processing you want to do. You have to do either batch processing, which means you wait for your data to come in, and then once you have all the data, you process the data. Or you can do stream processing, which means as data comes in, you process your data. But it's really difficult to do both at the same time because all the tools and frameworks around big data processing, they do either batch or stream. But Apache Beam is trying to change this. It's trying to give you a single model where you can do both batch and stream processing, and that's what I'm going to talk about today. All right, but before I do that, what I want to do is, first of all, I want to give you an overview of big data processing at Google and talk about how big data processing evolved at Google, and then from there we'll get to Dataflow, because Beam came from Dataflow. So I'm going to talk about Dataflow model and Dataflow service, and then finally we'll take a look at Apache Beam and see how Dataflow evolved into Apache Beam. So big data processing started with what's called MapReduce. I'm sure most of you know what MapReduce is. There was a paper on MapReduce back in 2004 that explained how to do big data processing on multiple machines. So what you do is, first, you have lots of data. If you can process the data on a single machine, then you don't need MapReduce, you don't need Dataflow, you don't need anything, actually. You can just do everything on a single machine, and it's nice and simple. But when you have lots of data, it's not feasible to process that data on a single machine. So in MapReduce, what you do is, first, you chunk your data into smaller chunks, and then you map this data on different machines. So these machines, they apply some kind of mapping function. So they transform the data using this mapping function. And then from here, you send this data to other machines. So you shuffle them. And then these reduced machines, they will apply another aggregation to your data, and then you will get your result. So it basically involves mapping your data, shuffling to reduction machines, and then from there applying an aggregation to get your results. So that's how big data processing started at Google. It started with a paper in 2004, and after that there was a lot of innovation at Google that happened after MapReduce. So if you look at after MapReduce, there's Bigtable, there's Millwheel, there's PubSub, there's Spanner, there's Flume. So these were all papers, or there were internal implementations that we had at Google. So they weren't really available to people. But just to let you know, some of these things are now available. For example, PubSub, it's publish subscribe messaging that we used to use at Google, but now it's available to people who uses Google Cloud. Similarly, Spanner is another technology where we used a long time at Google, but now we are making it available to people as well. But at the time, these were either papers or internal implementations that we only had access at Google. Now, at the same time, people at Apache, they looked at these papers and they started creating open source implementations. So, for example, Hadoop came along. Hadoop is the open source MapReduce implementation, and there were other things like Spark and Pig and Hive. So basically, there was an ecosystem of open source projects that came into being after MapReduce. So because of this split in innovation, we actually have two products at Google to support this. So all the big data innovation at Google ended up with something called Cloud Dataflow that I'm going to talk about. But at the same time, if you are using open source projects like Hadoop and Spark, and if you want to run them on Google Cloud, we have something else called Cloud Data Proc. So Cloud Data Proc gives you a Hadoop or Spark cluster in 90 seconds, and you can run your cluster using that. And then once you're done with your job, the cluster goes away, and you only pay for what you use. So because of this split in innovation, we have two products to support two different ecosystems. So MapReduce is great, and it solves a lot of problems, but usually you don't use a single map and a single reduce. Usually what you do is you chain multiple map reduces together because your data is complicated, so sometimes you do a map and then you do a reduce and then maybe you do another map afterwards. So what you're doing is you're basically building a pipeline. So people within Google realized this, and then they created something called Flume Java. The idea of Flume Java is that instead of thinking in terms of map and reduce, you start thinking in terms of data pipeline. So Flume Java provided the high-level APIs for you to define what your pipeline is and what kind of transformations you want to apply on that high-level API. And under the covers, Flume Java uses MapReduce. So it looks at your pipeline and it tries to optimize your MapReduce, and it tries to run it for you in an efficient way. But as a developer, you're not really thinking in terms of map and reduce. So let's just take a look at an example. So imagine you want to compute some mean temperature from some data. First, there's this notion of P collection in Flume Java. So P collection is basically just collection of some data. In this case, it's sensor event. So there you have some sensor data coming into your system. Now, let's say you want to parse this data into location temperature pairs because you want to be able to calculate mean temperature per location. What you can do is you have a parsing function that takes your raw data and parses it into location and temperature. But you can also wrap this into something called pardo. Pardo stands for parallel do. And what it does is basically it takes your parsing function and it applies that in a parallel way. So you're basically doing this parsing on multiple machines in parallel. So at this point, you have your raw data extracted into this structured input. And then to get the mean out of that, what you can do is you can apply a mean function. So you apply the mean function, and you can do that per key. So you're basically taking each location, and you're applying a mean function on each location. So you're basically getting the mean temperature for each location. And in the end, you want to write raw results. So what you can do is you can just say output apply, and there's many sources and sinks in Flume Java. So one of the sinks is writing to big table, but you can write to many different places as well. So that's how the Flume Java API looks like. One thing that you realize is that we are not thinking about MapReduce anymore. We are thinking about P collections and how we can apply different transformations on that P collection. And under the covers, Flume Java transformed this into multiple maps and reduces, and they're optimized map and reduce. So that's Flume Java. And after Flume Java, people started using it within Google, and then they started processing a lot of data. But at some point, when data gets really big, you need to divide that data into different chunks. So one way of doing that is basically divide it, like, say, per hour or per day or per week. For example, if you have some kind of log data, you can maybe divide your logs per day. So you have logs for Tuesday, Wednesday, and Thursday, and then you can process each day separately. So that's one way of dealing with big data. But and this is called batch processing, basically. So you have lots of data, you divide that into smaller chunks, and then on that chunk you do some kind of processing to get your result. But batch processing, it works in some cases. Like for example, if you are doing payroll processing, payroll usually happens once a month because people usually get paid once a month. So it works perfect for batch processing. But in other use cases, it doesn't work at all. So imagine you want to do anomaly detection. So you want to be able to detect if someone is trying to break into your system. If you do batch processing, if you process your data at the end of the day, it's too late because the person already broke into your system. What you want to do is you want to be able to detect that right away so you can take action. So batch processing doesn't work all the time because of latency. The second scenario where batch processing doesn't work is sessions. So at Google, we have users, and with users, you have sessions. But sessions, first of all, sessions have gaps because people come online, they do some stuff, and they go away. And secondly, sessions don't break down into days in a nice way. So if you look at the users here, there's gaps here, and then but there's maybe no gap here. So trying to do batch processing on session data, it becomes really complicated. So what we have is basically continuous data coming into our system, and we want to be able to process that data as it comes in. That's the reality that we live in today. So what can we do? One way of dealing with this problem is that you can create two separate streams from your data. In one stream, you can do stream processing. So as data comes in, you process the data, and you get some results. But these results, they will be approximate. They won't be full results because you don't have the full data yet. So without full data, you can only give an estimate. So data comes in, you produce some estimates, and as more data comes in, you update your estimates. Now, in the other stream, what you can do is the batch processing. So you can feed it to the batch processing pipeline, and then you can store all the data for, let's say, for 1 day. And at the end of 1 day, you can calculate the full result for the whole day, right? And then this way, you can have estimate data from the stream processing pipeline, but then you can have accurate final data from the batch processing pipeline. So this kind of works, but as a software engineer, I don't like this model because now, instead of dealing with one data flow, you're dealing with two separate streams, and then you're doing batch processing and you're doing a stream processing in probably different kinds of machines and probably different kinds of teams. So you're basically duplicating your work so that you can do this kind of stuff. And at Google, we also had something called mill wheel. So we realized that we had to do stream processing, and then people basically created mill wheel. There's a big data paper on this as well that you can read about. But basically, just like Flume Java, mill wheel provided high-level constructs to define a streaming system, and it took care of all the details of how to run that streaming system for you. So you don't have to worry about that yourself. So when we look at streaming, there are certain things in streaming that are really easy to do. For example, if you want to apply some kind of filtering, so element-wise transformation, some filtering to your data, you can easily do that because the data comes in, you have a function to run, you run that function. If the data needs to be filtered, it's filtered. If it's not, then it goes through, right? So that's very easy to do. But if you want to do some kind of aggregation, if you want to calculate something, then you have to actually chunk the data, because if you wait in streaming systems, the data is continuous and unbounded, right? So if you don't chunk the data, then you will wait forever to calculate something. So at some point you have to decide how do you want to chunk the data so that you can calculate individual chunks and see what they have. So for example, in this case, we have the data coming in. We will chunk it per hour. So every hour we have a window, and then we will apply this aggregation function for that window and produce some kind of results. Now, you can do this as you see the data. So when the data is produced and then it gets to your system, then you can do this chunking and then aggregation at that point. But usually that's not what you want. Usually you want to use the event data. So the time that the actual event happened, that's the time that you want to use in your aggregations. Because imagine you have your mobile phone and then you're playing a game and then you send an event, but you're offline, you cannot send that event. When it gets to the server, it can be hours or even days afterwards, right? So you want to use the time that actual event happened rather than the time that it took to get to your system. So there's this notion of processing time and event time. Event time is when the event happened, and processing time is when the event got to your system. So you usually want the event time to be your aggregation, but you receive the events out of order. There's no guarantee that the events will arrive to your system in order. So what you have to do is basically you have to reshuffle your events so that they're in the correct place in the windows, and then you can do aggregations in those windows. Also, sessions they're still problematic because in sessions you have users that come online and then offline, so there's gaps, and then you have to do reshuffling again with sessions as well, because users might be offline, and when they come online they send the event, but it might be an event for yesterday, for example. So you have these gaps that you need to deal with. So at this point we need to talk about what's called water flow. So there is this event time that I talked about, and there is this processing time that I talked about. If all the events got to your big data system right away, so if there was no latency, then everything would be on this ideal line. So this is when the event happened on your cell phone and it got to your big data system right away, then all the points will live in this ideal line. But in reality, we never have this, because in reality, we have networks and we have latency. So by the time the event happens and by the time it gets to your system, there's a time difference. So in reality, the line kind of looks like this. So this line is sometimes close to the ideal, and sometimes there's a skew between the ideal and the time that you actually receive the event. And this line is called Watermark in streaming systems. So Watermark is basically an estimate that system keeps track of to see how delayed your events are. Because in streaming, the data is unbounded, so you need to have some kind of notion of how late my data is so that you can use that information to emit results. So in big data processing and in data flow in general, there is this notion of watermark that it keeps track of, and it tries to use that as an estimate to see how late things are. So now, so we have different trade-offs at this point, right? If you want completeness, so if you want full and accurate results, you need to do batch processing. There's no other way around it, because you need to see all the data and you need to calculate all the results so that you can get completeness. Now, if you want latency, if you want low latency, if you want to see results right away, then you need to do streaming, because in streaming you process things as they come in, but then you give up on completeness a little bit because you don't have all the data yet. And then you also need to think about cost, right? If you want to process things as fast as possible, then you need to use a lot of machines, but then that becomes expensive. If you don't want to use that many machines, then it's cheaper, but the things will be delayed. And then there's this fundamental question of, you know, streaming or batching. Like, you need to decide that up front. But why do we need to decide that? Why can't we have both at the same time? And the answer is yes. That's why we have data flow. So in data flow, the whole thing of data flow is it's basically a one unified model that tries to unify stream and batch processing, so that you don't have to make that decision up front. You can use the same model for both, and we'll take a look at that. So in data flow, there are 4 basic questions that we are trying to answer. So first one is, what are you computing? So are you doing sums? Are you doing aggregations? What are you trying to compute? The second thing is, where in event time results are calculated? So how does the event time affect the results? The third thing is, when in processing time are results materialized? So when do you actually emit results in your pipeline? And the last one is, how do refinements relate? So if some data comes late, what do you do with it? Do you add it to your result, or do you discard it? What do you do with that? So let's just go through these in order and see what they mean. So in terms of what are you computing, Dataflow provides some primitives. The first one is the element-wise transformation. So you can take some elements and you can transform them to some other elements in some way. And you can do this in parallel. So you can do par-do. You can wrap this in a par-do, and this way it happens in parallel in multiple machines. The second thing you can do is aggregation. So you can take a lot of elements and you can aggregate them into fewer elements. You can use group by key. You can use combine, and there are some others as well. And there's also composite transformations. So in here, you are basically combining your element-wise transformations with par-do, and you can do count. So you can basically combine things together. And we'll take a look at some examples of this. So imagine that we have a game that we're playing on our mobile phone, and then it calculates some scores, and we want to calculate the score or our team using Dataflow. So let's just take a look at that and see how that looks like in the code. So first, we read the events, the log lines of our game from somewhere, and we get a P collection. So remember, Flume Java also had P collections, so Dataflow basically uses the same notion. Actually, most of Dataflow's APIs, they are influenced or directly copied from Flume Java. So you get a P collection of your data. Then next, what you can do is you need to parse the data. So just like before, you have a parsing function that takes the data and extracts team and score pairs from that. But then we do that in parallel. So we wrap that into a parallel do so that we can do it in parallel. And then you can do an aggregation. So in this case, we are basically taking we are aggregating per key. And here the key is the team. So we are basically combining all the scores for the team. And then we are doing a sum of that. So that's what we are calculating here. And this way, we have the scores of teams and their total score. So as you can see, this is very similar to what we had in Flume Java, and that's not an accident. We actually use a lot of that here in Dataflow. So if you look at an example, so this is an event time, and this is the processing time. And this is our imaginary ideal line where everything should ideally live on this line, all the events. But in reality, this doesn't happen, so you can see events all over the place. So if you look at this point, this event happened around 12:06, but it arrived to our system at around 12:07, which is not bad, so it's close to the ideal. But then if you look at this point, this happened at 12:01, but it arrived to our system at 12:08, so it's quite delayed. So if you want to calculate the sum of our team, what you can do is, in typical batch processing, you basically go bottom up. So as you see points, you add them, and when you see all the points, you have the result. So you basically emit the result in the end. So we are going basically from bottom up all the way, and then in the end, when we've seen all the data, we emit our result. So this works, but one problem with this is that you have to see all the data before we can emit a result, right? We have to wait for all the data to arrive before we can see the result. This works with limited data, bounded data, but if you have unbounded data, it's not going to work because you will always have data coming in, right? So you can't just wait for the data forever. So in that case, what you can do is you can do windowing. So you can actually take your data and break that into smaller chunks so that you can do aggregations on them. So windowing is optional in batch processing, in bounded data, but it's not optional in unbounded data because otherwise you won't produce any results. And there are different kinds of windowing that you can do. You can do fixed windows, so that these are just windows with fixed size. You can do sliding windows where these are windows that are fixed size, but they overlap each other. Or you can do session-based windows. So these are windows with users that might have gaps in them as well. So to apply windowing in Dataflow, what you do is you basically take the same code, but then you apply a windowing function before you produce your result. So you can say window into, and then I'm using a fixed windows in this case, and I'm specifying my duration. In this case, it's 2 minutes. So I'm basically dividing my data into 2-minute chunks. So with this, what we get is something like this. So you can see that we are dividing our data into 2-minute chunks, and then we are producing 4 results instead of 1 result. So for every window, we have a result. This is good. We have more refined results now. So instead of 1 number, we have 4 numbers. But we still have the problem of emitting results until we've seen the last data. So we have to see all the data before we can emit results. So it doesn't really solve all our problems yet. So to control how to emit data sooner, we can use the watermark. So remember I told you about watermark, and watermark is the heuristic that the system keeps track of to see how delayed the events are. So we can use the watermark as a guide to figure out when to emit the results. So to do that, we can change our code to this. So we are still doing windowing, but then we're going to trigger as we pass the watermark. And by the way, this is the default that you have in Dataflow. So even if you don't specify this, it will trigger at the watermark. So that's what we are doing here. And with this, this is how our pipeline looks like. So forget about this one, because this talks about perfect watermark that we never have. But if you look at here, you will see that, for example, in here, as soon as we pass the watermark, we emit 5. And as soon as we pass the watermark here, we emit 22. And then in here, in the last one, we wait longer because the data arrives later. But basically, we also emit result as we pass the watermark. Now, this is much better because, for example, 5 is emitted much earlier than others. So we don't have to wait for all the data to emit results now. So that's good. But the problem in this case is that we are omitting this one, right? Because what happened is that we passed the watermark, but then this data arrived much later, and then we just dropped the data. So that's not that great. Thankfully, in Dataflow, there's other things. There's these things called early and late firings. So you can basically specify, trigger a result at the watermark, but also trigger some early firings, which means speculative results. So you want to see results as they come in. So you can do that with early firings, and you can also do late firings. So you can specify what happens if some data arrives late. What do you do with that? So in this case, we are triggering at watermark, but we are saying that we're going to do early firings at period standard minutes 1. So every 1 minute, we're going to emit a result as a progress indicator, basically, to tell people that this is how we are progressing to our final result. But then we're also adding a late firing, and then this time we are using a count. So we are saying that if one piece of data arrives late, just do a firing for that as well. So with this, what we have is something like this. So we do an on-time firing for 5. And then for this one, for example, first we do an early firing as 7. And then we also do another early firing as 14. And then finally at 22, as we pass the watermark, we do a 22 on-time firing. So this way, you can see how your windows are progressing with early firings. But at the same time, when 9 arrives late, you don't drop it because there's a late firing, so it will be fired as well. So you include it in your result as well. And then the last thing that we want to do is how do refinements relate? So if something arrives late, what do we do? Do we drop it? Do we add it to existing sum? All that kind of stuff. So in this case, we are basically adding something called accumulating fire panes, which means that if there's a late firing, include that in my results, so don't drop it. That's what this means. And there's many others as well, but this is just one of the examples. So once we add this, basically, when 9 arrives late, we'll add that to our result. There will be a firing, and that firing will trigger a sum, and we will add that to the result. So if you think about it, we started from classic batch, then we did batch with fixed windows, then we did streaming with watermark, then we did streaming with early and late results, and then we did streaming with accumulations. So there's all these different models, and usually you implement these with different kinds of systems. But with Dataflow, by just changing a couple of things here and there with the model, it gives you that richness so that you can do this kind of very different data processing in many different ways. So that's what Dataflow is. Now, let's talk about now Dataflow, the transformation of Dataflow to Apache Beam. So far, we talked about Dataflow model, so that's what I described to you. And then there's also a Dataflow SDK, a Java SDK, but there's also a Python SDK. So that's what Dataflow model and SDK is. So that's kind of like the client side of Dataflow. There's also something called Google Cloud Dataflow service. So this is a service that runs in the cloud. It's fully managed. And what you do is you create your model, give it to Dataflow service, and it will run it for you. It will create the machines. It will run things in parallel, and then once it's done, it will write the results, and it will shut down your cluster. So it's a service where you can run these models. So what we did at the beginning of 2016 is that we donated the model and the SDK to Apache Foundation, and that created what's called Apache Beam. So everything I talked about, Dataflow model and Dataflow SDK, it's now Apache Beam. So Dataflow is only a service now, and you can write your pipelines with Apache Beam and run them on Dataflow. And the great thing about Dataflow, Apache Beam, is that, first of all, it has all the things that Dataflow has, and now it's called Beam Model. It has SDKs, so it has a Java SDK and also a Python SDK that's almost as good as Java, except it's not 100% yet, so it's getting there. But for me, the most exciting part of Beam is that it has runners for different things. So you can write a model, a Beam model, and run that against Dataflow like before. But you can also run it against Flink and Spark, and also you can run it locally as well. So it gives you a one model, basically, that you can run against different kinds of pipelines that you have, whether it's in Apache Flink or Apache Spark or Dataflow. So the vision that we have for Beam is that you would write your model in any language you want, and then that will give you a model, and then you would run that against any pipeline you want, and then you will get your result. So that's kind of like the vision that we want to have with Beam. Now the reality of today, as of March actually, is you have a Java SDK today. There's also a Python SDK that's 80% there. It still needs some work on streaming for Python SDK. Then once you write your model, you can pass that to Cloud Dataflow, of course, but then you can also pass it to Spark, Flink, and Apache Apex. And there's also another one that's coming up. And then the runners themselves, they're only in Java right now, but there's also a Python runner that's being written. So, and this is a community project now, and Google is contributing to it, of course, but there's also a bunch of companies that are contributing all the different runners. And if you want to see another SDK supported in some other language, you are welcome to contribute as well. All right, so let me just show you quickly how this looks like. What I want to show here right now is, let's take a really simple example, run it locally, and then run the same example in Google Cloud Dataflow and see how portable things are with that. So let me make this full screen. So if you go to Beam's website, there's quick starts for Java and Python as well. If you look at the Java quick start, there's a word count. So this basically looks at some files and counts the words in those files and saves them. So it's basically, it will just produce words and the number of times that word happened. There's a Maven target that you can run. And this is some of the code. It's a little bit hard to see, but basically this is the main method. And then in the main method, you create a pipeline with some options. And then you define what happens in your pipeline. So there's certain steps. You read the lines, then you count the words, then you map elements with some formatting function, and then you write the counts. So it's basically read, do some processing, and then write. If you look at counting the words, it does what I showed you before. It gets the lines, and then it does extract from those lines in a parallel way using pardo. And then we format the results. So we take all the results and put it in Word and the counter words format. So we use format as text for that. So that's what the code is like. And you can run this locally. So there's a local runner that you can use to run your app. So I just do Maven, and word count is what I'm running. And then the runner itself is direct runner, meaning it's a local runner that I have running. Now, the pipeline is running locally on my machine. And if we actually take a look at the folder, we'll see that we have some counts. And then if we take a look at these counts, these are the counts that we just calculated from a single file. So we look at the single file, and from there we calculated some counts with words and their counts. So this is running locally, and you can take the same pipeline and run it against Spark or Flink or Dataflow. And actually, if you go here, it shows you all the different ways of running it against different things. So for Dataflow, we just copy and paste the Maven target. And when we run it, a couple of things to note. It's basically word count, and then I'm running Dataflow runner, and I'm also pointing to my project. And then I'm also pointing to the location of the files that I'm processing and the output of the files where I'm going to save the results. In Google Cloud, you save results to cloud storage. So I have my files in cloud storage, I read them from there, and then once I'm done processing, I'll save them to cloud storage. So I run this. Now this is submitting a job to Google Cloud so that we can run it in Google Cloud. If you go to Google Cloud Management Console and look at Dataflow, you will see that there are some jobs that have been submitted, and this is the job that I just submitted right now. That's running my job. If you click on it, you see your pipeline. So it's read lines, do work counts, format them, and write them. And you can get some stats about your job as well. See how many things you're processing and stuff like that. And if you go to Google Cloud Storage, there's a bucket for my app. And under this bucket, you see some counts. And if you click on the counts, we'll see some counts or words. So everything is, so the beauty of this is that this happens in the cloud, and it happens on multiple machines in parallel, but I don't have to deal with machines, I don't have to deal with clusters. It just, Google Cloud does the work for me. All I do is define my pipeline and my model, and then just let things run, and in the end, I have my results. So that was just a quick example to show you. And the last thing that I want to talk about is, so when you think about it, we are basically trying to build an abstraction layer on top of Spark, Flink, and Dataflow, and other things. So we are trying to combine all of them into this single unified model. So how do you do that? There are a couple of ways of doing it. First, you can look at Spark and Flink and Dataflow and say, okay, this is all they do. All of them, they do this. So let's just take this intersection of their functionality and call this Beam and be done with it. This works, but it will be very limited because we want Beam to be much more than just the intersection of all these products. Another way of doing that is you can look at all of them and just combine everything into Beam. So Beam would be like a kitchen sink of all these products. But this is not good either because there are certain things in Spark that doesn't make sense in Dataflow, or there are certain things in Dataflow that doesn't make sense in Flink. If you combine all of them together into a single model, then it won't feel natural, so it's not going to work either. What we are trying to do is something like this, where we are trying to influence these different products into Beam models. So the Beam model is influencing Spark, and Spark is influencing Beam model as well. So we are trying to basically transform them so that in the end, people will have no reason to use just Dataflow or just Spark or just Flink. They will just use Beam model because it's rich enough to support all these different products. And then they have everything, basically you have everything you need in Beam to do whatever you want. You just pick your runner and decide where you want to run it. That's the thing that we want to achieve. And there's also a website with capability matrix that tells you, given the things in Beam, which ones are supported in Flink and Hadoop, Dataflow and Spark and Apex, stuff like that. So if you want to write a pipeline, it's good to check and see what is supported where. And this is always updated as people work on things. All right, so basically I showed you this at the beginning, where we had two sets of innovations that led to Dataflow that I talked about, and then it led to things like Hadoop and Spark that you can run with Cloud Dataproc. With Apache Beam, we are basically trying to combine these two worlds into a single model, and that's why I like Apache Beam, because it tries to unify things rather than divide them, and hopefully in the future it will be a single model that people use no matter where they're coming from. All right, that's all I have. Thanks for your attention. If you want the slides, this is my Twitter. If you want to know more about Dataflow, this is the link, and then this is the Beam page, and there's also an Apache Beam Twitter.